All
But
right.
yeah, thanks for having me. So as I said, I'm the chief of product over here at Multiverse Computing. Um, and so what I wanted to spend today is first just introducing the company Multiverse Computing to our audience, and focus on a couple of our products, our low-level products that might be of interest here. Um, so yeah, let's dive right into it. So who are we at Multiverse? So we're a quantum software company. We're globally recognized. We're a global company itself. I'm here based in Toronto, but we have offices. Our biggest office in Spain, in San Sebastian. We have an office in Germany, in Paris, France, in the UK, and like I said, here in Toronto, our next biggest office. But not just being located globally, but being recognized globally. Last year, we got a nice accolade from CB Insights saying that we're one of the top 100 AI companies in the world to watch out for. So while we are, we present ourselves as a quantum software company, that's really just about how we achieve what we do using quantum technologies. But what we offer is really in optimization and in AI, which I'll dig into later into the talk. We're a growing company, so we have currently, I think, around 140 employees. From when I joined a couple of years ago, I was employee 20 or something like that. So we're growing fast. We're very productive, having a lot of papers, a lot of patents, and a lot of partners in industry to develop our software and to create solutions that are relevant today to industry and to generate value today. So we hear a lot about how quantum, it's still nascent. It's maybe 5 or 10 years when we have those fault tolerant computers. That's when we'll be able to generate value with these things. But here at Multiverse, we found that actually with today's technologies, we can find those opportunities for generating value in industry. Um, while some of them can be particularly niche, it's important for anticipating when that huge boom around quantum will happen when those fault tolerant computers arrive. So where other quantum companies, you might hear them talking about quantum advantage a lot, we talk instead about business advantage because that's what's really of interest to our clients, our customers, our partners is what value can be generated for that business using today's technology. So here's just examples of some of the partners that worked with and many different areas. So we can see we have applications at all sorts of different industry verticals from starting out in finance, but we've branched out into manufacturing, into energy, healthcare, cybersecurity, all sorts of things. And you can see probably some recognizable companies in here. Bank of Canada is a big one if you're here in Canada. A lot of European companies as well coming out of our office in Spain and in all of these different areas. So how are we able to offer so many different applications across so many different verticals? So this is how we're set up. So up in the top corner, Singularity. This is what we refer to as our entire software suite. So it's the Singularity software suite, not just one individual product, but a collection of many products. And then Singularity can be bundled into to different vertical focused packages like Singularity for Finance, where we have all sorts of financial applications, portfolio optimization, index tracking, FX trading, derivative pricing. But then we also have Singularity for manufacturing, Singularity for energy, for cybersecurity. And what allows us to have all of these many different use case applications is that they're all based leveraging the power of our core foundational engines, our foundations products in optimization and in AI. So two of those core pieces that we show on the slide here, and which I'll dig into one of these in more detail in a second. But we've got Singularity optimization. So this is a low level generic optimization package. It's available in Python, but other interfaces as well. And with this package, developers are then able to submit kind of a standardized, generalized optimization problem for solution by quantum approaches. So taking a specific use case problem like portfolio optimization, and then our developers then style that in a particular mathematical form that can be submitted into this generic solver, singularity optimization. We get the raw result out of that, and then again we reformat it back into the context of portfolio optimization. So it's really these core engines that are doing the big heavy lifting. And then that allows us to have all sorts of many different use case applications using today's quantum technology that are based on this optimization and machine learning routines. So it's another one we have listed here, singularity of machine learning. So using quantum machine learning techniques, quantum deep learning techniques for all sorts of different applications within these different areas. These core engines themselves, they're also available as standalone products. So for other low-level developers that resemble the internal developers that we have at Multiverse, so those people at Multiverse that are using these core engines to develop these use case applications. And then, of course, we have a lot of developers here that are building these core applications, and that's where comes in all of the quantum engineering and a lot of tensor network engineering, which I'll elaborate on a little bit. So we do try to, for our end user applications, so including our core packages, and then especially, of course, our use case applications, we try to avoid anything that requires any sort of quantum expertise. So we don't include much quantum jargon at all, other than to say, like, yeah, it's powered by quantum techniques, quantum computing. But we try to make a package like SLP or singularity optimization familiar to people who are used to optimization software, but maybe really unfamiliar with the world of quantum. Similarly with machine learning, and of course with something like portfolio optimization, we don't require asset managers to have a degree in quantum physics to be able to use our tools. So who we do require to have quantum degrees are developers in-house at Multiverse, and they're the ones that are connecting our software to various quantum hardware that's available from our partners, including Xanadu, but also D-Wave, IBM, IonQ. And then we have a lot of in-house specialists on tensor networks. So this is referred to as a quantum-inspired computation approach. So if you're unfamiliar with tensor networks, this is a method of computation that was developed in recent years out of physics departments as a way to efficiently simulate quantum systems within conventional hardware setup. So what it does is, with using tensor networks, what you can do is sort of reduce that full Hilbert space, your 2 to the n giant space, down into a little corner by making certain approximations representing your quantum objects, your quantum states, using these tensor network objects. And then those approximations allow it to represent just that one corner of the Hilbert space where things are actually kind of useful and interesting, like near the ground state, or showing certain symmetries that are relevant to the problem. And then that way we don't have to consider that whole Hilbert space, which is the massive bottleneck when trying to do quantum simulations on a conventional hardware. And then the idea is that, well, if I can use quantum systems to do novel computations, then why can't I use an efficient simulation of a quantum system to do computations? And so that's what we apply here at Multiverse. We have some of the world experts on tensor networks here at Multiverse, and we've been able to come up with some really novel and powerful routines in these two domains of optimization and in AI that not only act as a stepping stone for when real pure quantum hardware can kind of catch up with the capabilities in terms of number of qubits that it can handle and all of that, but then tensor networks is itself really driving forward a lot of what can be done in computation, powerful computation. So just like where tensor networks are quantum inspired, and we can then develop algorithms out of that, at a certain point when quantum starts to catch up, I imagine that a lot of those developments are going to be inspired by developments that happen in tensor networks in this near term right now. So we're very comfortable with leaning on tensor networks and considering this as part of that quantum atmosphere. Now, knowing the audience that we have here at QHack, I would imagine that this is kind of the level that definitely the QHack participants would be interested in developing at this level, connecting directly into quantum hardware. Whereas, like I said, our packages that we develop are intended more for users who don't necessarily have that quantum expertise, but do can benefit from the power of it. So we have maybe about 5 minutes left. So I wanted to just quickly zip out of these slides that I prepared and instead switch over to some actual code that I can show you. And so here I'm going to demonstrate an application of singularity optimization on an example of an optimization problem. So here you can see the package that I'm using. So I'm in a Python framework for this presentation right now. So we import singularity optimization module. So you'll see it throughout the code represented as SOP. And then the problem that we're going to be tackling is an analog to the traveling salesman problem. So if you can see this computer chip circuit, so imagine that you're working at a computer chip production company, and you need to drill holes in this computer chip, and then the next one comes in, you need to drill holes in that, and so on and so on. So you want it to be done as efficiently and quickly as possible. So I need to drill all of these holes that are marked on the board, and then I can automate, okay, what order should I drill these holes in? And so then it becomes, like I said, it's pretty much that traveling salesman problem. So I need to have my drill visit each of these locations once and exactly once. So I can't go back to the same place and drill a hole again, because that would just be inefficient. I don't need to drill it twice. But all of these holes do need to be drilled. And this is actually a computationally challenging problem. It's well known that traveling salesman is difficult. And so what we do in this example is we style the problem as a QUBO. So many of you might be familiar with that. So that's quadratic, unconstrained binary optimization problem. So that's one type of standard format that optimization problems can be represented as, one that's most directly applicable to many quantum routines, like the Ising models underlying quantum annealers like D-Wave, but then also variational approaches using gate-based computers, QAOA, will work on solving QUBO type problems. So if I quickly speed through here, so you can see some of the code is first just representing the problem. Okay, what are the different drill speeds in the different directions? Let me give you a function to determine the distance between each of the points. Next here comes in SOP, so I'm just going to declare, instantiate the variables, my binary variables, since we're creating a QUBO problem, although I can do integer variables with SOP as well. So here the way that we're doing binary variables is that, all right, so for every position, I'll have a variable based on its location, and then also what position is it in. So if I have that spot that I need to drill and I label it number 15, which would be the job, is that the first drill hole that's drilled? Is it the second? Is it the third? Is it the fourth? And so on. So then I would have a binary variable for each of those. And then only for spot number 15, only one of those should be 1, the rest 0, which would indicate, okay, for that one variable that's a 1 and not a 0, then that would indicate that job 15 happens at that stage in the sequence. Now, using that, then I'll zoom down here, and I use these variables to construct a cost function. So the function that I'm trying to minimize, which is the total time spent for my drill moving around. So that includes the distances between each of the drill spots, and then these different variables, whether or not that drill spot happens at that time, yes or no. So that's 0 or 1. So this is what we refer to our objective, or our cost function, which we're looking to minimize. But a really important part then is putting those constraints. So if I just minimize this cost function, well, very easily I can just set all variables to 0, and then that would definitely minimize it, but this would not be a viable solution. Right? That would be telling me, hey, don't drill any holes in this hole. So we have a lot of constraints that also get submitted along with it. So each job needs to be done exactly once, and at each point in time, I can only drill one hole. So those constraints then get combined with the objective into an optimization model. So this is like a pretty familiar approach to coding for optimization type problems. You'll notice that there isn't mention at all of anything quantum in here. It's just, hey, what's your objective? What are your constraints? All right, let's use our quantum solver to do it. So we've prepared this model. Now we're going to optimize it using our quantum inspired method. And then just sort of print the results. We have another method in here using a greedy solver technique just for comparison. But well, I'm running out of time in this presentation, so I won't actually, run this code right now. I can jump to some results that presented earlier, or prepared earlier, sorry, before this call. So you can see here, okay, running the circuit, we'll start, or the drilling. This is the optimal path that comes out of it from our SOP tool. So hit all of these locations in this order. So we've got it plotted out here, but of course it comes out as a convenient dictionary or list, or however the user might want to style it and integrate it into their own workflow. Okay, so I know it's a short time to try to present Multiverse and all that we do, but I hope that this was a good representation of those things and it captured your interest. But with that, maybe I'll wrap up and pass back to Isaac for the Q&A portion.
Cool. Thanks a lot, John. That was really interesting. Thanks so much for that. We had some questions, so let's try and get to them here. We had a question from Entayido. John, what is the sample or data size of the file for the optimization of the SML approach?
Right. So we can handle very large problems. The size of the problem with our particular SML routine, or at least one of the classification routines that we have in mind, that I have in mind that we use greatly, it's not the data set that is represented with quantum bits. So our machine learning techniques, I'll step back a little bit. We use a hybrid approach, and we use hybrid approaches in a lot of what we do. Because of the limitations that exist in current technology, quantum technology. So like with our machine learning, our quantum enhanced boosting technique, there's one intermediate step that's carried out using quantum techniques, but then the rest are still using classical conventional approaches. So with that classification thing, it's not limited then by, or like the quantum step is not limited by the number of the data set. It's more about the accuracy of the model that you want to come in. So it's an ensemble learner approach, and so it's like the number of weak learners that are represented by qubits in there. So that's kind of the limitation. So, but going, up to excuse me, losing my voice, up to 100 or more qubits, we can definitely handle that.
Cool. Okay. There's a couple questions that are coming in right now. Like, how do I begin with the qubit model in finance, or like, what are the resources? Where can people go to learn more about Multiverse?
First off, go to our website, multiversecomputing.com.
Okay.
We have a lot of literature that's available on the archive. So you could go straight to the archive. You can go to our website, and all our papers are listed. And while some of our things we keep close to the chest, so we don't share all of our proprietary techniques, but many things are shared in that literature, including how we, for example, take that portfolio optimization problem and represent it as a qubit. Honestly, that was the thing that got me so excited about Multiverse when I read that paper. So my background, I come from condensed matter physics, so I'm familiar with the Ising model. And then I worked for a number of years in finance, so I'm familiar with portfolio optimization. And then to see, oh, wow, portfolio optimization represented in the Ising model. And then I could just do this by finding the ground state of that. And I got super excited, just rushed over to the Multiverse.
Yeah, definitely. The Ising model can be applied to like 7 million things. Like, right. This was like right at the start of the pandemic, but I even thought I saw like a paper about like something about COVID-19 and like the transverse field Ising model. Somebody wrote a paper about that, and I had a good chuckle over that. The transverse field Ising model has been beaten to death. Okay, question from Kentucky Kirby. How does Multiverse interface with, or does it interface with other packages like Qiskit or PennyLane or anything like that?
Yeah, so that's the part where I was talking about like behind the scenes within our core engine. So that's the work that our internal developers take care of. So having this generic interface, and then we like to say that we're hardware agnostic. So in the back end of our tools, then we prepare all sorts of different routines so that we can very easily swap out the different solvers for our end user, who can just select from a drop down menu or keyword argument. So then in that back end, if we're using Xanadu or whatever, or IBM's computer, then we can have things based interact with PennyLane or via Qiskit. We do have on our roadmap too, and whether how interesting this is to potential users can sort of accelerate that on the roadmap, but having allowing those deeper low-level quantum engineers to interact with our products so that they could themselves be working in a Qiskit environment and make use of our tools and sort of integrate things at that end user level as well.
Cool. All right. Well, that's all we have time for. But John will be on the Discord after this as well. So if you do want to have a chat with John over the course of the duration of QHack, please do so. John, it was great to have you on here. Have a great rest of your day and enjoy this. Looks like the sun has disappeared for us here in Toronto, but enjoy the rest of your day.
All right. Back at you. Thanks very much.
Cheers.